Good morning, everybody. Today is the final day for quantum factoring. We're going to wrap it all up. I'll remind you of everything that we've done, but I also wanted to just say that really in the first lecture we kind of saw it all. I mean, we saw the idea for why it works, the plan, and really in the preceding lecture and this lecture, we're just proving some mathematical facts that seem pretty plausible and indeed turn out to be true. So on one hand, I'm a little bit sad. I'm we're going to take another lecture to prove all the details. But I'm a theoretical person. I really want to see all the details of why it's exactly right. So we're going to wrap things up in this lecture by doing that. But I think it's good you can even focus on just the first lecture we did about quantum factoring, and you'll really have the main knowledge you need to know about it. Okay, so let us recall how it all worked and what we still need to do. So we are trying to make an algorithm with a quantum computer that factorizes an enormous number with thousands and thousands of digits. And for simplicity, we assume that it just has two prime factors, p and q. And this is the plan for the algorithm. So we're going to choose a base of an exponent, which I'll call b. And you can usually use 2. And so we mostly talked about 2. But just to remind you of the full details, I wrote b here. And the main goal is to consider all the powers of b mod n, 2, 4, 8, 16, always mod n. And you want to find the first one that wraps back around to 1 mod n. And then you've sort of found all the powers of 2, or b. And the main goal is to figure out what is L, the number of such powers of 2, or b. Okay? And that's the part you need the quantum computer for. And it's known once you can get that, what you can do is try to compute x, which is b to the power of half of that L mod n. And then once you do that, then usually you can get the prime factors by computing the GCD of x plus or minus 1 with n. We saw that last time. And occasionally, this doesn't work because either L is not even, or sometimes this step doesn't work. It just gives you back n and 1 rather than p and q. But you can prove, and I guess we didn't have time to do it in this course, but anyway, it's just a lot of number theory. It's not too hard. You can prove that if this doesn't work, then if you just pick a different b, it might work. And you can prove that if you just start picking b's at random, I think there's either a 3/4 chance or a half chance that any random b you pick will work. So you really just have to maybe repeat this plan 2 or 3 times at most, and you'll get the prime factors. Okay, so I should also mention that this plan was known long before quantum factoring algorithm existed. They knew this in the 70s and 80s that the problem of factoring reduced to this problem of finding L. But then they're well, we don't know how to solve this problem either. Okay, so the quantum algorithm for finding L, how does it work? Well, we make code for this simple operation multiplying by 2 or by b mod n. And that's a permutation on all the numbers, in particular on all the powers of 2, or b. And so we let R be the associated quantum operator for it, the unitary operator for it. And we're assuming this number capital N has little n digits. So normally you would, or let's say binary digits. So normally you would just have it operate on the number encoded with n digits, a1 through an. But for some reason, there's a mathematical trick that makes it just a lot easier to analyze if you just put in one extra qubit that is not operated on. Last time I also called that b, and then when I was writing these notes, I was wait a minute, there's 2 things called b. That's a bad idea. So now I'll just call it a n plus 1. Right, so the plan for figuring out L was to do our key quantum subroutine, rotation estimation, on this unitary, capital R, which sort of cyclically permutes the powers of b, or the powers of 2. And rotation estimation needs a start vector, which in the greatest case is in one of the 2D planes of rotation for R. And then if you manage to set that up, you'll just get back the angle of rotation for that starting vector. Unfortunately, in this problem, we don't know how to find a vector that's prepare a qubit, your qubits in a state vector that's in one of the 2D planes of rotation. So we're well, the only one we pretty much know how to set up is just 1. That's the simplest power of b. Then we have to tack on this extra bit because of this extra qubit here. And so the plan is to just, use that as a starting vector and like cross our fingers that something good happens. And what we eventually showed is that this rotation estimation, this unitary operator that cyclically permutes the L factors of, or powers of 2, or powers of B, actually has like L planes of rotation corresponding to like a 1 over L fraction of the circle, a 2 over L fraction of the circle, a 3 over L fraction of the circle, and so forth. So all these rotation angles that look like K over L times tau, that's 2 pi or 360 degrees, a full circle. These are rotation angles. And what we need to show, in fact, still, is that if you start with this starting state and do rotation estimation, then this starting state has like an equal amount in each of these different planes of rotation, and therefore, we'll show, you get each of the possible rotation angles with equal probability. So in short, the output of this is this thing that I call the clue. It's like, lots of digits of a random fraction. You can always divide by this tau if you want. A random fraction with L in the denominator and K in the numerator. And, we would love to know, like, for example, just the fraction 1 over L or 2 over L or something, but we get this random clue. But then I tried to illustrate to you that actually just a few clues like this suffice to figure out L. In fact, we didn't quite do it this way, but it's not hard to show that if you just get, if you know that L is at most n digits long, and you get 2n digits of this random fraction, there's an efficient algorithm that just figures out what this fraction is in lowest terms. And that's more or less enough to get you L. The only thing that could go wrong is like if K, let's say L is even and K is also even, then when you take this fraction to lowest terms, maybe this gets divided by 2 and this gets divided by 2. So you get, maybe you learn L over 2 in the denominator. And this is why you have to take like a couple of clues, and you basically, find the lowest common denominator for all the clues you got, and that's very likely to be L. Or you could do it how I illustrated before, where you like take a couple of these fractions, and you just try to do the GCD on them, and you'll get out both of the fractions. Okay, so what have we done and what have we not done? And then in this lecture, we'll do the parts we haven't done. Okay, we have like 90% figured out the planes of rotation for R, and I'll review that. And indeed, they have angles. Well, let me say it here. We discovered L planes of rotation for R with angle 0 over L of a circle, 1 over L of a circle, 2 over L of a circle, and so forth. And that's great. And there's one little technical piece of this that we hadn't finished showing yet, though, which we need, which is that these planes of rotation are perpendicular to each other. So again, it's the sort of thing that ought to happen, but we need to check it. So we'll do that in this lecture. And that's sort of everything, by the way, because I should have read this first. R actually operates in like 2 to the power of n plus 1 dimensional space, some huge space. But we're going to, like in the algorithm, we're going to sort of start applying it to this vector that looks like a power of b here. And, basically we just apply R to this piece a bunch of times in some sense. And so we never really generate any states that don't look like a power of 2 or a power of b here. And then like, 1 qubit here and this like extra bit. And there are only L, by definition, powers of 2 or powers of b, and this adds a factor of 2. So like all the action of the whole algorithm is happening in like just 2 times L out of all the dimensions. And therefore, like once you found like L 2-dimensional planes of rotation, you're like, that's everything. Like I found like the whole, full understanding of R. So as I said, the last thing we have to check, which we didn't quite check, is that these L planes of rotation that we found are perpendicular to each other. So they're kind of like a basis of the space where all the action of R is happening. And then the other thing we have to check in the second half of this lecture is this last bit. Like we know what happens if you do rotation estimation with like a starting vector that's in one of the 2D planes of rotation, but now we're doing it with a starting vector which is some kind of equal combination of all the planes of rotation. And we need to check that indeed what pops out is like a random one of these angles. Okay, so that was the plan, and we're going to get into verifying those last 2 pieces today. Right, so what were these planes of rotation for R that we discovered? Actually, for every angle like this, integer fraction of L times 360 degrees, we actually found two perpendicular vectors which form a basis for this plane of rotation. And for whatever reason, we called them these like steering wheel states. And we subscripted them by the angle, which is like KL over tau. And then there's just this one and like a 90 degrees rotated one, a perpendicular one, the steering wheel state. And they look like this. So let me remind you what's going on here. These are 2L dimensional vectors. But rather than conventionally listing them like a column of 2L numbers, we like listed them like here's the first two coordinates, then here's the second two coordinates, here's the next two coordinates, etc. And rather than writing like a two-dimensional vector as like two numbers, we're like, oh, well, let's draw it as a vector. So it's a bit of a funny way to depict it. But this one always starts out with a horizontal vector, so it's like 1, 0 is like the first two coordinates of this one always. And then like the subsequent vectors are like rotated clockwise by theta, then 2 theta, then 3 theta, then 4 theta, etc. And because this theta is always like an integer fraction, like integer over L times 360, like once you get to the Lth one, and you like do one more, it like exactly perfectly wraps around. And this is sort of why it had the special property that it was like a vector which R rotates in like a two-dimensional plane, and it wraps around to itself in L, or sometimes fewer than L, like if L has factors, many steps. And the perpendicular vector that was also in this same plane of rotation was just pretty much the same thing, except you start out like pointing up, and then like this is 0, 1, and then it again rotates by thetas. Okay, so that's where we were. And we did check, by the way, that these two things are perpendicular. These two things have dot product 0. So like we found, like for each plane, we found like a nice perpendicular basis for it. And now the main thing that we have to check is that the different planes are themselves perpendicular. And there's like no hand gesture I can really make that like can depict that, because in our three-dimensional world we cannot have two perpendicular two-dimensional planes. So you just got to use your imagination. I mean, you can have a 2D plane that's perpendicular to like a 1D line. That's the best you can imagine. But you have to imagine like perpendicular two-dimensional planes. So in some sense, what we need to show is that like if you take any vector from, let's say, this theta plane, let's say this one, and any vector from a different plane that has like a different angle, then those two vectors are perpendicular. So that's what we're going to show in the first part of this lecture.